Okay, let's talk about generalized least squares models and how to actually fit them in R. So we're going to go through a specific example here. So I have some data. This is global warming data that estimates northern hemisphere temperature from 8 climate proxies. And so each observation here represents a year of data from 1856 to 2000. So just knowing that information, knowing that each observation is from a year, what do you think could go wrong if we just use ordinary least squares? And particularly thinking about what could go wrong in terms of the assumptions that we make about error. So anytime you've got data that is collected over time, you need to be somewhat concerned that you're going to end up having correlated errors. And so in particular, here we would expect that from year to year, there's probably some correlation between temperatures. And so if we have a very cold year 1 year prior, then it's likely that the next year is also going to be cold. Sort of how we expect that these things are correlated. And so you want to take into account that correlation, which of course is what GLS is good for. So let's talk about how we would do this in R. So I'm using the global warming data. It's called Globe Warm. It's from the Faraway package. And the first step I'm doing here is I'm just omitting the NA values or the missing values. And this is because basically this data set contains values for predictors all the way going back 1,000 years, but it only has an outcome variable for the past 145 or so. One thing to keep in mind, this class we really don't go over how to handle missing data other than to note that it's there and remove it. But in general, when you're doing kind of advanced data analyses, and as you move forward as statisticians or analysts, you'll want to sort of be very careful about what you're removing and what that could mean. And so in this particular data set, removing values doesn't actually have a negative impact because we are explicitly saying that we're only looking at a subset of years, and we happen to be removing years that don't fall into that subset. And so there's not really a risk of removing these missing values. But if we were missing values kind of meaningfully throughout the rest of the data set or throughout years, which we said we were accounting for, that would be bad. And so, or it could be bad. And so you might want to do something more sophisticated. So it's always important before you just delete your missing values that you sort of think about what they mean and what the implications could be for removing them. All right, so I've gone ahead and created a new data set, globe warm underscore, that doesn't have any of these missing values. And now I'm just going to fit our ordinary least squares, our linear model, using the LM function. And so NH temp is our outcome variable, the northern hemisphere temperature. And then I've got these 8 predictors that I'm using to predict it. And so our concern here is that the errors are correlated. And as we've mentioned, kind of a proxy for being able to determine how the errors behave is to look at the residuals. And so what I've done here is I'm just looking at the correlation between the residuals lagged by 1 year. So essentially this takes the residuals from that model and it removes the first one. So it looks at years 2 through n. And then this looks at the residuals, but it removes the final year. So this looks at years 1 through n minus 1. And so what this is doing is just taking the correlation between a year and the subsequent year's residuals to sort of see if there's some correlation there. And it looks like there definitely is. Our correlation here is 0.58339, which indicates that there really is some strong correlation from year to year. So fitting a normal linear model is going to violate this correlated errors assumption. So we're going to have to do something a little bit fancier. So how would we actually fit this using generalized least squares? Well, you all in the last class very expertly derived this. I was really proud for those of you who've already uploaded your application exercises. Those look great. So we would fit this by basically estimating sigma. So we're going to estimate that big sigma that basically tells us the structure that we're expecting from this correlation between these errors. And then we'll use that to be able to fit a model that shows that incorporates that correlation appropriately. So If we assume the errors take this simple autoregressive form, so basically each error is correlated with the prior error, you can write that like this. And so this is the error I plus 1, and it equals some phi times the previous error. So this phi is going to be that correlation coefficient to indicate that these are correlated. And then, of course, you have some additional kind of error term here that we expect is normally distributed. And so we can estimate that phi from the model. And so that's going to be basically the correlation that we're estimating between the ith error and the ith plus 1 error. And so that's exactly what we calculated here, this 0.58339. So this is what we estimate that phi is. And so under this assumption, then we know that this big sigma here, we can write this as equal to, so sigma ij, the ith row in the jth column is going to be equal to phi raised to the absolute value of I minus j. So that's what we can build our sigma matrix using this exact equation. And that's directly based on how we're assuming that this is correlated. And so what I'm going to do here is I'm taking that linear model that I fit, and I'm pulling out the design matrix, X. So this is just going to be, instead of creating that design matrix by hand, I can use model.matrix to pull it out. And then to create sigma, I'm going to start by creating just a diagonal matrix. And so this is just going to be to sort of fill in this matrix to start with. And so I want to have a matrix that has that is n by n. And so we had calculated a variable n back here that's just the length of the residuals, which is equivalent to the number of observations. And so this diag n is just going to create basically an empty sigma matrix where we have 0 on the off diagonals and 1 on the diagonals. And now I'm going to fill it in with this equation that we've specified here. And so phi is going to be that 0.5833 that we estimated here, that correlation. And then I'm going to raise it to the absolute value of the row of sigma minus the column of sigma, so I minus j. And so that is our sigma, our estimate for sigma here. And so now what do we do with that? Well, let's pull out the y variable. So this is our outcome y. I'm just getting that from my global warming data set. And now let's calculate the inverse of sigma because we're going to need that. And we can plug that into the equation that you derived for beta hat. And so I can pull out that sigma inverse. I can create this x transpose x inverse that includes that sigma sandwiched in between the x's. So I've taken the inverse of sigma. I've made this x transpose sigma inverse x inverse matrix here. And now I can plug that into a beta hat equation. And so this should be the exact equation that you derived for beta hat when you derived this in the last application exercise. And so this is what this results in here for the coefficients for this model. This is what we get. And so we can check what the correlation is now. And so we can look at the residuals by calculating y minus x beta hat for this model. And I can look at the correlation between the residuals if I lag them. So I've basically taken off the first residual and then taken off the last residual to be able to look at what the correlation is between the ith residual and the ith plus 1 residual. And now it's similar to what we had before, but it's a little bit different. Now it's 0.588. And so the process by which this happens is basically, if you were doing this by hand, you would keep iterating this process where you find a sigma matrix that you estimate based on some structure that you assume, and then you would estimate that phi based on the correlation that you're observing. And then you would fit it, and you would refit it, and you would refit it until you kind of converge on a correlation, basically until you'd set some convergence criteria such that when it stops changing at some rate, then you would stop fitting your model. So you would keep doing it until you kind of saw some stability in that correlation. And so that is kind of how you would do this by hand, of course, but you don't necessarily have to do that. And I'm going to be showing you in just a second how to do this using a package in R, so you don't have to do that iterative process. Now there's another way to do this using the S variable or the S matrix that we had talked about in class as well, and you also derived parts of this. And so that S, again, is kind of like taking the square root of sigma using this decomposition method. And so there's this Cholesky decomposition, which you can use the CHOL, the chol function in R to be able to calculate that. And so that's kind of like the equivalent of taking the square root of that sigma matrix. So once you've calculated sigma, you can get S from that. And then, of course, we can get the inverse of S. And then we multiply that inverse times X, and we also multiply that inverse times Y. And so this was that X prime and Y prime that we talked about last time in class, and we showed that, in fact, you can just regress these two quantities, so these prime quantities, and you'll get the correct answer. And so that's what I'm doing here. I've got this Y, SY, tilde SX, and so basically I fit this regression model on these X and Y prime values. And then this -1 is just because SX is going to have an intercept already in it. And so I don't want it to be fitting an intercept there. So that -1 will make sure it doesn't fit an additional intercept. And so these are the values we get here. And in fact, we can compare those to the ones we calculated by hand. And you'll see that you get the exact same values. And so we get the exact same values here when we do this by regressing these prime values that we calculated using that S matrix as we do when we calculate that beta hat by hand that you derived. So this kind of just is a gut check that this is all working like we would expect it to. So that's how you would do this by hand. But it turns out there's a package in R called NLME for fitting nonlinear models like this, and you can do this. You can use this package to be able to fit things like generalized linear or generalized least squares. And so here is an example of that. So the syntax is going to look really similar. This is going to look exactly the same. Of course, instead of LM now, we've got GLS. We have the exact same equation. The data is exactly the same. And the one thing that changes is we've added this correlation line here. And so in this particular case, because we think that this is, we talked about how this was sort of a simple autoregression where we're just lagging by 1, we're going to use the core AR1 function to indicate that that's the kind of correlation, the structure that we expect. And there are all kinds of different structures that you could put on this, but this is the one that would allow us to lag by 1 year like we did in the previous example. And so we're going to set the form equal to tilde year to indicate that the thing that we're lagging by is the year. So that's the variable that we think is driving this correlation. And so this is the output we get from that. If you'll notice, these values look very similar to the ones that we had estimated when we were sort of working through this by hand. And right here, this parameter estimate phi, that's going to be the estimate for the correlation that was estimated based on this 1 year lag. So it's estimated to be 0.71, which is pretty high correlation, but kind of makes sense because you would expect year to year that the temperature is really going to be highly correlated with itself. And so we can actually calculate a confidence interval on that using the intervals function. If we set which equals to var-cov, or var, this is sort of for variance covariance, it'll calculate a confidence for that phi value, confidence interval for that phi value, and it ranges from 0.5 to 0.8. So those are pretty high. I would say that we could feel pretty confident that there's definitely some correlation going on between these errors, and we did the right thing to fit a generalized least squares model here instead of just the normal least squares, especially if we're interested in doing some inference on this model. Now, to note in all of this that there might have been even a better way. So there's lots of different correlation structures. I think your book mentions the ARMA structure. Maybe that would have fit this particular data even better. So there's other ways to sort of think about fitting these models that can be more sophisticated even than what we're showing right now. But it's important to sort of at least keep in mind and think about whether or not errors might be correlated. And when you are dealing with any kind of data over time, that's certainly a concern. So some other examples, so we've talked about autocorrelation here where, for example, when you have data over time, you expect them to be correlated. Other ways that errors can be correlated, grouped data, or your book talks about block data. The example I like to always give here, I think we talked about this a while ago when we were talking about independence, but when you think about, for example, a study that looks at eyes, how if you enroll 10 people and each person has 2 eyes in the study, and you kind of perform some operation on these eyes, or you apply some medication to these eyes, if you treat that as 20 independent observations, you would expect that you would likely get the wrong answer. So this is kind of like thought of in sort of like a grouped or a blocked type of design, where you would expect there to be some correlation between each of these people. And there are sort of other sophisticated ways besides this generalized least squares to deal with this type of data as well. That if you take a categorical data class, you'll likely get into some of that. I know our categorical data class gets into it specifically through mixed effects models and things like that. So then the final way, I mean, these are not exhaustive, but another common way that you can end up with correlated errors is via spatial data. And so that's like if you are looking at data over space, like for example across the United States, you would expect there to be correlation between space in that case. And so sometimes we think about this, for example, even in polling data, when people are thinking about for the election, kind of whether or not states are going to be highly correlated. And there are a lot of different ways in which states are going to be highly correlated. But you would expect that even geographically, there might be some correlation there as well, especially for folks kind of right on the borders. Okay, so for your application exercise, what I want you to do is use the cheddar data, which is also in the faraway package, and I want you to run the code below to add a time variable. And so we're going to add this time variable that basically assumes that the data that is in this data frame was collected over time sequentially. And so we don't know if this is true or not, but let's pretend like it is, and let's try to see if we could, if that were the case, if we would be concerned about some kind of correlation, or whether maybe that's not as much of a concern. So what I want you to first do is just fit a normal linear model predicting taste from the 3 remaining variables in the data frame. And then I want you to plot the residuals from that model against time and sort of determine whether you see anything, if you see a pattern or not. And then after doing that, I want you to fit a generalized least squares model using this AR1 correlation and determine from that if there's evidence of correlation between the errors.